What is up, everybody? Welcome to the 10th lecture of Math 131. Today we're going to be talking about probabilities and expected values. To start off with, we should probably get some definitions out of the way. First, what is a probability? Well, a probability is the measure of how likely an event is to occur. Cool. Next, we want to talk about a sample space. A sample space is the collection of all possible outcomes of some experiment, some sequence of events, whatever we might be looking at. After that, I want to talk about what an event actually is. An event is just a subset of our sample space. Having said all that, there are two different versions of probabilities that we might be talking about. We might want to talk about theoretical probability, or we might want to talk about empirical probability. Empirical probability is just what we measure. So let's say we run an experiment and we see something occur 4 times out of 7 experiments. Well, the probability of that thing occurring as we measured it would be 4 out of 7. We observed it occurring 4 times, and we took a total of 7 observations, so 4 divided by 7. Theoretical probability is a little bit more involved. Really what it is saying, in theory, these are the number of possible ways E could occur, our event. These are the number of all possible outcomes as well. That's what NS is. So let me step back a little bit. Theoretical probability is just what you see here as a definition. We're taking and counting the number of ways E is likely to occur. And then we're taking and counting the number of ways our experiment as a whole could end. We're saying that the probability of E occurring is the number of times E, or the number of ways E could occur, divided by the number of ways that our experiment could end. This is abstract. Let's look at a more solid example. Let's consider we're rolling dice. We've got just one die. All sides are labeled 1, 2, 3, 4, 5, 6 accordingly, right? Let's say we want to look at the event of rolling an even number. Well, that could occur if we roll a 2, a 4, or a 6. So there's 3 different ways that that could occur. 3 different outcomes to that particular event. So our sample space, denoted typically with an S, is a set of values 1, 2, 3, 4, 5, and 6. And our event is the set of values that are even values out of our sample. So in this case, 2, 4, 6. And the probability of rolling an even number is going to be the number of values inside of our outcome, or our event as E, divided by the number of values in our sample space. So 3 divided by 6, or 1/2. We have a probability of 1/2 of rolling an even number on a dice, on a die. All right, so this is theoretical probability of rolling an even number on a die. But let's say we run an experiment and we observe E occurring 14 times. But the total number of observations or experiments that we run is, let's say, 34. Then the empirical probability of rolling an even number would be 14 out of 34. So empirical probability is the measured occurrence of a thing. And theoretical probability is the calculated occurrence of a thing. It's what we're predicting will happen. So having said this, why do we care about probabilities at all? Like, what use are they to us? Well, other than understanding things like the success rate, the probability of a medical procedure being successful, understanding the news, being useful for a night at the casino, or 1,000 million other things. 1,000 million. Someone's going to hit me for that, I'm sure. But other than all of these other things, we could also use it to predict things like, or to calculate things like expected values. So the next question then is, what is an expected value? I'm happy you asked. Before we move on to expected values, I want to touch really quickly on this idea of the law of large numbers. What the law of large number tells us is really just exactly what this definition says, obviously. What it says is, if you do this experiment a bunch, the measured empirical probability is going to get closer and closer and closer to the theoretical probability as you do it more and more and more. And we see this all the time. Think about flipping a coin. We might, for the first 8 times, find that that coin lands in heads 6 times out of the 8. Well, we know, though, that this isn't actually representative of the probabilities of getting heads or tails. We also know if we do this 1,000 times, we're probably going to get a lot better, we're going to find an empirical probability that's a lot more representative of this theoretical probability. It's going to get closer as we do it a bunch. Again, it doesn't have to be that way, but that is the tendency as we do more and more and more and more experiments. Having said that, let's move on to expected values. So an expected value is just really a tool to say, hey, what can I expect the outcome to be? What can I expect the value of this experiment to be if I do it a whole bunch? And the reason why it has to be done a whole bunch is because we use the theoretical probability to calculate the expected value. And because the empirical probability approaches the theoretical probability over a bunch of iterations, we're going to have to do a bunch of iterations before we can say we can expect the value to come out to be what the expected value is. So, this is weird, I know, and I'm going to show an example in a few minutes. Before I do, an obvious question shows up. Why do we care? Why should you as a student care about any of this? Care about it because this shows up actually quite literally everywhere. This is how companies determine what products to sell and where to sell them. How investors determine what to invest in and what not to invest in. It's used by scientists and researchers all the time. It's used by the court system, by insurance agencies, by literally everyone. And more often than not, this is one of the easiest ways math is used to be weaponized against us, right? To do things against our best interests. Well, I'm not going to insure person A because they have this pre-existing condition and the probability is it's going to cost me more money in the long run. So the reason we should care about this is to prevent it from being weaponized against us. This is one of the most useful tools in everyday life when making decisions that there is. I shouldn't say it's the most useful, but it's one of the most useful. Having said that, how do we find expected value? Well, the first thing we need to do is figure out a way of converting all of our outcomes to numbers. And I just realized I misspelled convert, I forgot the T. Oops. So the first thing we have to do is convert all of our outcomes to numbers. It's really kind of a step 0. After that, we multiply the outcomes with the associated probability of that outcome, and then we add all of those products together. So let's look at 2 different examples of how we might use this. For our first example, let's consider rolling a die. We want to know what the expected value is going to be if we roll a die a whole bunch. Well, our sample space, pretty straightforward. It's going to be 1, 2, 3, 4, 5, 6. Okay. So since we don't have to turn these into numbers, because they're already numbers, right? We can go straight to setting up the table to help us calculate the expected value. So we set up this table with a column for outcome, a column for theoretical probability, and a column for products. Now what we're doing is we're saying if the outcome is 1, well, the theoretical probability of rolling a 1 is 1/6. Matter of fact, theoretical probability of rolling any number on a die is going to be 1/6. So we can multiply 1 and 1/6. We're going to get 1/6. 2 and 1/6, 2/6, so forth and so on all the way down. Then we're going to add all of these up. We're going to find we get an expected value of 21/6, or 3.5. So what does this 3.5 tell us? What does this mean? What this means is, if we're going to roll this dice over and over and over again, and we took the average value of all of those rolls, the more we do it, we should expect the average of those rolls to get closer and closer to 3.5. This doesn't mean that we're going to get 3.5 on a roll. It means that the average roll, if we do it a whole bunch, is 3.5. So there's a bit of a distinction there, right? All right, cool. Let's move on to this other example. This other example, we're going to flip a coin 4 times. 1, 2, 3, 4. In each flip, our coin can land on heads or tails. We want to know what the expected outcome is of landing on a head if we flip these 4 times each set of experiments. So the first time, first 4. Second time, second 4, so forth and so on. So heads, tails isn't really our sample space here. Our sample space is the number of times we land on a head. The number of times we could do that would be 0, 1, 2, 3, and 4 times. All right, so our sample space is the space of how many times we land on a head in each consecutive 4 flips. That means in our table over here, our outcomes are going to be 0, 1, 2, 3, 4. And our products are going to be 0, 1 times 4/16 is 4/16. 2 times 6/16 is 12/16. 3 times 4/16 is going to be 12/16. 4 times 1/16 is 4/16. So, adding these together, we're going to get 32/16. Or 2. So if we flip a coin 4 times, what this expected value is saying is we should expect it to land on heads 2 times. Which jives with what we know, right? If I flip a coin, I should expect it to land on heads half the time, and tails half the time. So if I do this a whole bunch, I should expect out of four flips, the coin to land on heads 4 times. Now you might be asking yourself, where did I get these theoretical probabilities? Perfectly normal question to ask. This comes from what we're going to talk about in our next lecture. In the meantime, if you have any questions, by all means, please feel free to shoot me an email and ask. I'd be happy to help. Have a good one, guys.